Hello, Honor Chem students. So this is your first honors topic about significant figures. Honestly, it's a very annoying thing, but it's something you gotta learn as if you're trying to do more advanced chemistry. And hopefully this will give you kind of an idea of like why we bother. So significant figures, most of the time we just say sig figs. All the cool kids say sig figs. It just refers to the number of digits, to the digits in a number which show the precision of the measurement. So that's really like the utility of this, like why it matters. We're showing how precise a number is. And hopefully it will become clearer as we go through these examples, like what precision means, but we're basically like saying how exact we know a number. If it has only a few sig figs, it's less precise. If it has lots of sig figs, we can be more precise about our numbers. And this kind of matters more because if we're trying to make a claim about a measurement, if I'm trying to do a calculation based on a measurement, I can't say my answer is more precise than like the measurements I actually took. Because that doesn't work. Like that would be making a claim that I don't have evidence for. We have to match our precision to our starting values. So like, here's a little example. This math is something we'll practice a lot more in the future. It's called dimensional analysis. It's when you use a conversion factor, like a fraction, that gives us an equivalence, like 1 mile is equal to 5,280 feet. Conversion factor, a way we convert from feet into miles. Anyway, we'll practice that a lot more in the future, but this is just one strategy for converting units. So if I want to change 500,000 feet into miles, so I do my little calculation and I get like this number on my calculator. And so it's kind of tempting to want to write down all those digits because, I don't know, they're all there. Maybe you want to round it to like the tens place or something like that. But because this number was like not very precise, like it was like 500,000, like, but like the odds that like it was exactly 500,000, and I'll tell you later how we tell, but this number isn't specifying that it was exactly 500,000. So if that number wasn't precise, what we started with, I can't report this as my answer because I don't actually know that it's exactly 49.69 miles. I would instead report it as 90 miles. Equally less, not very precise beginning number, not very precise ending number. And again, I'll tell you how to like actually count these in a sec. But let's kind of talk about the concept of precision and about like about sig figs before we have to do any math and counting. So we have these two situations. We got A, so I have like a rock or something. Yeah, I have a rock. I have rock A, and I measured rock A on 4 different balances. 4 different balances. And then I also measured rock B on 4 different balances. Same rock on all of the balances, but as we are going to see soon, we got different numbers for the rock depending on what balance we put it on. So let's look at this. So we want to determine how closely the mass can be determined with each balance. So econobalance, let's look at that one first. So for B and for A, we're looking at these numbers. When I measured my rock, how many digits were we able to get with this balance? To what like place were we able to measure the mass? So we got 100 grams and 200 grams. And you might be saying, oh, well, it's probably like exactly 100 and 200, but looking ahead, we can kind of see that that's not true. For this balance, it's only measuring by hundreds. The answer was rounded to like the nearest 100. And we know that because like I can see as I look at my future ones, like this one knows it's 140, but I did 100 because it rounded down on this one. So different tools give us different amounts of precision. This balance is only able to round to the nearest 100 grams. Let's look at our next one. So now we got our good balance, this guy. Again, what place is this answer being reported to? Like, how many digits do we get in our answer? We got 180 and 140. It's rounding to the nearest 10 grams. I don't know it's exactly 140 because there's no future decimals. There's nothing to tell me that it's actually that precise. It's only rounding to the tens place. Got balance pro. We added another digit, so now we got 177 and 143. So what digit are we rounding to in this one? We're rounding to the nearest gram in this one. Okay, now finally we got this one. And again, we've added another digit. So what place are we rounding to with this balance? Now we have our 10th place. We're rounding to the nearest 0.1 grams. So like looking at these different tools, this is the idea of precision. These tools are giving us more precise measurements. We know for sure that there are more digits versus this one, since it's only rounding to the hundredths place, less precise tool. So with that in mind, which one do you think is like the best quality instrument? Which one would be the best one to use? Which one do you think would probably cost the most? I'll let you answer this one on your own. Reach out to me if you want help with it. Okay, let's think about this. So if I had a new rock, new dealio. If I had rock C, does rock C, and I'm measuring it on my economy balance. So using this tool, I put a rock on it and I get a reading that it's 200 grams. So it kind of looks like this probably. I put a rock on it and it is reading 200 grams. So, and then the question is it smaller or the same size or bigger than sample A? So if I had like another balance that says 200 grams and I compare it to sample A, can you tell which one's bigger? Can you tell if sample C is bigger or smaller than sample A? So we have 100 grams, 200 grams. Are you able to compare them? So think about it. Are you able to compare them? So think to yourself, pause if you need, come up with an answer. Can you tell which one is bigger, smaller, or the same size, or can you not tell? So I'd encourage you to write this in your own words or something like that. But we had rock C was 200 grams, and we know that rock A is 100 grams. Comparing 100 to 200, I think we can all say that this one is bigger, right? So I think you can put that into words. I know it's like pretty clear on that one, but I can clearly tell they're different enough that like 200 is clearly bigger than 100. I can tell it for this one. Okay, let's think about this. So again, same situation. I have rock C, and I'm getting a reading that it's 200 grams, and I want to compare it to rock B. Can I tell which one is smaller or larger, or are they the same? So think about it to yourself for a second. Write your own answer if you'd like. I have rock C, which is measuring at that many, and I have rock B, which is measuring at 200 grams. So we're getting two readings that look like this, right? But is rock B actually 200 grams? Is rock C actually exactly 200 grams? That's the real question. So with this tool only, can we tell which one is actually bigger or smaller? Or can we be sure that they're exactly the same size? Answer is no, we can't be sure. Because as we saw with these examples, rock B is actually this many grams. We just weren't able to tell that with this tool, with this not precise tool. So the same thing could be happening with rock C. We don't really know. If this tool is rounding to the nearest 100, like rock C could be 150 grams, or it could be 240 grams, and it would still round to 200. We cannot be sure if they're actually the same, or if they're different, or which one's bigger. So something like that. Explain your reasoning. It is impossible to tell. So I'll leave that to put in your own words. Why is it impossible to tell? Okay, we got the mass of rock C is then measured using our other balances. So let's compare these results. Sorry, I have to keep scrolling up and down. So this is all data for rock C. We got balance, the econo balance is giving us that reading. So let's compare that to rock B. Also 200 grams. We still can't tell. Again, we can't tell which one is bigger or smaller. How about our good one, 180? Comparing it to rock B, still the same, but we can't tell. They seem the same. Let's compare to the Pro. Again, same number. But with this tool, let's see that. So X-Acto for rock C, we're getting 177.0 grams. The tool for rock B got 177.1 grams. So now that we know that, we can tell, okay, so we're comparing 177 versus B that has 177.1 grams. So comparing this number to this number, can we tell which one's bigger now? Yes. So rock C has a smaller mass than rock B. But we only are able to tell that because we're using this tool, because we're using a more precise tool. So again, I'll let you put that in your own words. So notice, this 0, the fact that we had that decimal place, the fact that we have that 0 at the end, was able to tell us that I have exactly 1.77.0 grams of rock C. That 0 matters. It is giving us precision. It is telling me that I am very sure about this measurement. It's adding precision. So that's kind of the concept of sig figs. We are going, I'll teach you how to count sig figs in a second, but a digit is significant if it adds precision. So any digit that adds precision is going to be significant. Any non-zero numbers are always significant. That's just like 15 versus 10, those aren't the same number. We gotta make sure it's the same number. But any 0 that makes it a number, so 100 versus 10, those zeros, they have to be there. They make them two different numbers, but they're not adding precision. They're just there. They're just making them different numbers. But 10 versus 10.0, suddenly I am sure, I'm making a statement using that decimal place, that both of these zeros are adding precision. It is 10.0, not 10-ish maybe. So if it's a zero that adds precision, it's significant. So there's a bunch of rules. People put them different ways, but like here's one way you can choose to think about it. Leading zeros, so zeros in front, before like non-zero numbers start. So these ones in bold over here. Zeros before our number actually starts. Those are never significant. Again, it's the concept of that makes it the number. 0.0004 is a different number from 0.04. It just makes it what the number is. It's not actually adding precision. So if I was to count significant figures, I would not count the zeros in the front. I would just count 1, 2, 3, my non-zero numbers. So this number has 3 sig figs, is what we'd say. Okay. Middle zeros, like some people call them trapped zeros, if they're in between 2 non-zero numbers, so like these guys, these ones do count. They're like a part of them, like they're trapped. If they're in between numbers, they always count. So in total, this number has 1, 2, 3, 4 significant figures. Okay, and I think the ones at the end are the trickiest ones. Again, there's different ways of thinking about it. I think this is probably the most straightforward way to sum it up. If the zeros are at the end, so after your numbers, like after all the non-zero numbers, if the zeros are at the end, but there is a decimal place, then they are significant. But if they're at the end and there is no decimal place, then they are not significant. So this one has 1, 2, 3, 4 significant figures. This one only has 1. I think this one's probably the trickiest again. So also just to clarify, like if I had that decimal place is telling me I'm like sure it's 50. It's exactly 50. So this has 2 significant figures. Or this 50.0 has 1, 2, 3 significant figures. Yeah. So it is just kind of annoying. It's just kind of one of those rules. I think thinking about precision kind of helps remember them, but at the end of the day, memorizing is probably going to be your best bet. So let's do some examples. I'm going to underline all of my significant figures and count them. So non-zeros are always significant, and then is this 0 significant or not? So we could choose to think about precision, or we can look back at our rules. It's an ending 0, and there's no decimal place. No like decimal, no dot. So it is not significant. So this only has 1, 2 sig figs. This one, we have ending zeros, but there's a decimal place. We are adding precision. It's exactly 3.00 kilograms. So I have 1, 2, 3, 4 sig figs. Here, ending 0, but with a decimal place. 1, 2, 3. Leading zeros, zeros before the number ever starts, don't count. Not a part of the number, not a part of precision. Just 1 significant figure. Ending zeros, but no decimal. Just 1 significant figure. Leading zeros don't count. Non-zeros always count. Ending zeros, and there's a decimal place, counts. Okay. So here's more of that kind of practice. I would recommend pausing the video and trying these ones on your own. Make sure you can count them all right. So recommend pausing right now, trying these guys. and I will show you how to do them when you're done pausing the video. Leading 0 doesn't count. Trapped 0 does count. 1, 2, 3, sig figs. Non-zeros always count. Ending with a decimal place counts. 1, 2, 3, 4, 5 significant figures. Non-zero, trapped, non-zero. Ending, no decimal place, 3 sig figs. Leading doesn't count, and then 2 non-zero numbers, 2 sig figs. These are written in scientific notation that hopefully you've learned about in your class. But same situation. We first, for scientific notation, don't look at this part, like that's not a part of the sig fig calculation. Only look at your main piece up in the front. So just looking at that front part, we have ending zeros but with a decimal place. 1, 2, 3 sig figs. And we have trapped 0 always counts. 1, 2, 3 sig figs. Okay, so that's counting sig figs. Something that takes practice, so I'd recommend, I'll have you have your practice problems that hopefully will help you get the skill down. So that's counting sig figs. And then, gets so much more fun. There's math with sig figs, yay. Again, more rules, it's great. There's only really 2. If you are multiplying or dividing, you round your answer I'm trying to think of how to phrase it clearly. To the least number of sig figs. From a starting number. Okay, so if you're multiplying or dividing, for figuring out how to round, you always look at your given, whatever numbers you started with. So in this case, we're comparing 3.1 and 2. That's my starting numbers. So when I get my answer, I'm going to look back at what I started with to decide how to round it correctly. So 4.0 times 2, plug that into a calculator, or like do it in your head, whatever. You should get 6.0, right? I always recommend just look at, if you're doing a more complex problem, like look at what's on your calculator, think about all those digits it says on your calculator, how many are we actually gonna write down? So maybe you wanna do this because it's 0.0, but to decide how to actually round this, we look at our starting number of sig figs. So in both things we started with, 3.0, 2 sig figs, 2, 1 sig fig. So whichever starting value had fewer, that's what you rounded to. So 2 sig figs versus 1 sig fig, we're gonna have to round our answer to 1 sig fig. So just 1, so our answer is only 6. 1 sig fig. Okay, so gotta get good at counting sig figs, and then you round your answer to your least number of sig figs. And of course, it has to be different if you're adding and subtracting. If you're adding or subtracting, you round to the least precise. Sorry, I keep having computer issues, but hopefully this is gonna work this time. I know that sounds like almost the exact same thing. It is very similar. It's slightly different though, so it's important to know the difference. What I mean by least precise in this case is that you want to round to least number of decimal places. Okay, so very similar, not quite the same thing though. So in this question, because it's adding, I am going to look at my number of digits. I got my 100th place and my 10th place. So when I go to write my answer, I want to round to my least number of decimal places. Not necessarily to 3 sig figs, to my least number of decimal places. So 10ths versus 100ths, I'm rounding to my 10th place. This is your answer. So I know they're very similar. Sometimes they overlap, but sometimes it matters that you know the difference. So let me show you one where it would matter. Like this. 522 minus 29. This number goes to the 10th place. This number goes to the 1's place. If you were using the multiplying rules, we would round to 2 sig figs. But we're not. We're using our number of, our level of precision, our number of decimal places. I want to round to the 1's place. So the answer to this question is this. Rounding to the 1's place. Not rounding it into 2 sig figs. Okay, so I know, very close to the same thing, not exactly the same thing. Okay, another thing to keep in mind. This will matter a lot more later. Conversion factors do not affect sig figs. So let me show you what I mean by that. A conversion factor, that would be if I want to do a question like this, where I want to change from one unit into another unit. What I use to do that is called a conversion factor. So like here's the conversion factor that I would use in this case. If I'm trying to go between inches and feet, it's probably helpful to know that 1 foot is equal to 12 inches, right? That's just called a conversion factor. So to solve this problem, and again, later in the year, we'll get way more comfortable setting up problems like this, but how I'm going to solve this is starting with my known 122 inches, and then I'll set up a fraction using my conversion factor with 12 inches on the bottom, 1 foot on the top, so that my units cancel. Again, we'll spend a lot more time with that strategy later, but this is going to be how I convert from one unit to the other. And if I plug it into my calculator, I'm going to get 10 point something, 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 something. But then how do we decide how to round this? You might be thinking, well, we just learned the rules for multiplying, and the rules for multiplying are that I should round to the least number of sig figs. So this has 1 sig fig, and this has 2 sig figs, and this has 3 sig figs. So I should round to 1 sig fig. No. Conversion factor is not a part of it. So I don't consider these ones. I only care about my starting value. It's basically because like the conversion factor is always going to be that. It's usually pretty precise or like pretty exact. It just isn't a factor. We only care about the precision of our starting numbers. So this has 3 sig figs. So I'm going to want to make sure my answer also has 3 sig figs. 10.2 feet. 1, 2, 3 sig figs. Okay. So yeah, that's it. Something you need to practice. I know it's annoying. I don't love it either, but it is what it is. Something I also wanted to point out as you're doing the practice problems, something people want to do a lot. If we're rounding for sig figs, we're just rounding the number. It should still be the same number. It's just rounded differently. So like in this case, we have 1 sig fig, 1, 2, 3 sig figs. It's multiplying, so we're going to round it to our least number of sig figs, which is 1 sig fig. So to show this number with 1 sig fig, I would round it to 2,000. It's not 2, because that's a completely different number. You just like I like doing it this way, underlining the like significant digits and then making the rest into zeros without a decimal place. Okay. So yeah, it takes practice. So check out those practice problems, turn them in on Canvas when you're done, or come get help from me. Reach out to me via email or come to seminar. But yeah, good luck with those practice problems, and thanks for watching.